Well, I think it's official. We can get started. Welcome back, everyone. So we're just about done with section 7.5. We have a couple problems we want to take a look at there. But then beyond section 7.5, we're really done with the real meat and potatoes of the course, which was chapters 5, 6, and 7. Chapter 5, we defined the functions. Chapter 6, we saw how to plot them. And in chapter 7, we've been dealing with lots of trigonometric identities, but all kind of culminates here in section 7.5. This is the purpose of most of the work we've been doing, just being able to handle and solve trigonometric equations when they show up. Beyond that, going into chapter 8, we're now looking at applications of trigonometry. And so one thing we're going to be doing starting in chapter 8 is using the calculator a little bit more. The math department is restrictive about some aspects of this class. As per the math department, the only calculators allowed in college algebra and trigonometry is either the TI-30X2S or the TI-30XA. I don't recommend this one unless you're really good at it because you've just been put through that a whole lot. Then keep on using that calculator. It's a decent one, but it is tricky to use unless you're really familiar with order of operations and that kind of stuff. This one's great because you can type a lot of stuff in one line. I blacked this out because we're going to practice what you would put in the calculator and all the keystrokes. And I would highly recommend this calculator here. If you don't have one, this would be a good one to pick up. It's probably about $10 at Walmart or even less, places like Staples potentially. What's that? Oh, gotcha. You should be okay because since we're only just starting section 8.1, we're not getting too far into it today. Again, if this calculator works out for you, this is not too bad of a one to get through. It has everything you need: sine, cosine, tangent. The keys above are not cosecant, secant, cotangent. Those are the three inverse functions that are most common, the ones that we actually studied as well. On this calculator, same kind of thing. You have sine, cosine, tangent. Sine inverse, cosine inverse, tangent inverse is the keys here. You just use the second button, hit sine, and now you're using sine inverse. If you wanted the reciprocal of sine, you would click the sine button, a power button, throw in -1, and that gives you 1 over sine, the cosecant. But we're going to look into those matters really carefully in chapter 8 when we start using calculators more and more. That means for the third exam, like we mentioned, this was going to be allowed on calculators. And same with the final exam. Calculators will be allowed on that one as well. Well, any questions, folks, before we jump back to 7.5? Okay, well, let's see where we left off. In section 7.5, we're solving just a couple more trigonometric equations. I forgot to actually open those notes. Here they are. And here's the equation that we left off on. Just as a review of what we're doing on this one, notice that the massive change in instructions, we're looking for only finitely many solutions, specifically in the interval from 0 to 2 pi. That means an answer to these problems is never a negative angle. And because of the parenthesis here, 2 pi is also not an angle that we'd ever give. We would give 0, which matches with 2 pi right at this terminal position. So we're only looking for positive angles along that range there on the unit circle. And that's why when we went to solve this thing, we first factorized it. We saw that this one had no solution. This is due to the amplitude being 1. That means any value on the right-hand side above 1 or below -1 is automatically not a solution to that equation. But on this one, 1/2 is no big deal because you can put 1/2 on the y-axis. Here it is, 1/2. You can't do the same thing with -5/4. It's somewhere down here. You just totally missed the unit circle, in other words. So 1/2 is conflated with angles 5 pi over 6, pi over 6 in this range from 0 to 2 pi. So our answer was done the moment we found those two angles. Any questions at all, folks, with the rundown on this one from last class?
I'm sorry, I forget. What is the difference between a bracket, like a squared bracket, and a parenthesis?
Oh, good question on that one. So when you put down a number line that goes like this, 0 to 2 pi, then the fact that we had a bracket right here means we were to shade this number line. we would put a solid dot right here to say 0 is a part of that set. Open circle here because 2 pi has been eliminated from the set. The shading would go this way. All numbers between 0 and 2 pi, 0 included, but the 2 pi, only because of the parenthesis right here, 2 pi is excluded.
So if that was a bracket though, we would include.
We would include it, absolutely. We'd have to fill in that point right there if there was a bracket.
Oh, thank you.
You betcha. The only reason we're excluding 2 pi is, once again, the angle 0 and the angle 2 pi both terminate right here. So if you're just reporting the angle 0, you have the whole story. You don't need to use 2 pi, 4 pi, 12 pi, and so on. Other questions about that so far, folks? Okay, well, this is example 2, part A. Looks like we have a couple more equations to get through. So here's the new one for today. We want to determine all solutions in the interval 0 to 2 pi like before. And this time we have cosine 2x equals sine x. This is really bad for a number of reasons. Let's mention the things we want. If we're solving a trigonometric equation, our hope of hopes is that there is one trig function. Maybe factoring can help us with that restriction if we can factor just right. But what's even worse is you want the angles to be the same. If you have 2x and x, that's a problem that should be fixed right away. We need to use a double angle identity right here to make this involve just x, not 2x. So let's make that our step 1. Use a double angle identity to make all inputs. By inputs, we mean the values going inside the function. The 2x and the x is what we're referring to as inputs. The same. If we can get all the same inputs, we're in great shape. And if we can write everything in terms of signs, even better. This is the moment where we would probably pause for a bit, go to, say, the trigonometric identities document, and do some soul searching. We need to find out, where do we have a double angle identity relative to cosine? Let's put this on a side-by-side kind of window. You could, absolutely. Exactly. And if you did that for cosine, what would actually happen is you're deriving this identity. That's how you prove this one right here, is you just use the addition formula, making this a theta plus theta. And this is the result. You get that result there. So you could use the addition formula or just jump down to the double angle formulas as well. But you know what? If I'm being totally honest, I wouldn't want to use this one. The reason is our problem has sine already. And this one involves both cosine and sine. It's just not really well suited to the problem at hand. Now, this one's no help either. It involves cosine. That's the one we want to use. Cosine 2 theta involving 1 minus sine squared theta. How do you prove that? Well, you just use the Pythagorean identity right here. Cosine squared theta is 1 minus sine squared theta. So you combine 1 minus 2 sine squared theta when you combine your like terms. So let's cite that identity and use it right away. Once I get the annotate to work, there we go. So cosine 2 theta is 1 minus sine squared. Let's call it this way, cosine 2x rather. We have x's in our problem. Is 1 minus, oh, messed up already. Let me try again. Control Z to the rescue. 1 minus 2 sine x. So we use that identity right there. Any questions, folks, with that? Oh, let me move that down. Any questions, folks, with that first step on this one? Okay, so we have actually doing the substitution in place of cosine 2x, 1 minus 2 sine x. Oh, excuse me, that's a sine squared. Let's double check that identity. It is a power two right there. Sorry about that omission. That is really quite important to have the power two. So 1 minus 2 sine squared x for the left-hand side, and the right-hand side we're just copying, equals sine x. So now our hope of hopes is to get sine in exactly one spot, but if you have sine squared, step 2, move all terms to one side and factor. You'll notice that factoring has come up a lot in equation solving, but that's par for the course, whether you're in any algebra class or trigonometry class or solving equations in calculus. Factoring is one of the massive methods that helps us out. So to get to that stage, let's decide to move all the terms to the right. I would probably want the higher degree term positive just to make it easier to work on. So 0 on the right-hand side, add 2 sine squared x to both sides. Sine x is still in this position, so plus sine x. And subtract 1 from both sides. So we have all terms to one side, 0 on the opposite side. Factoring is going to allow us to use the zero product property. So let's factor this next. Want to give it a lot of space? And let me know how this goes. If this is a confusing looking factorization, we'll try an analogy to help explain how we got there. Well, 2 sine squared x, we should try 2 sine x. Sine x to start. That's because if you multiply here to here, you get 2 sine squared x. Sine x by sine x gives you the sine squared. Next thing to take a look at is, due to this negative sign, this implies that we're going to expect a positive or negative as the inner terms. Let's go, I have a feeling positive should be here, negative should be here. That's just a feeling. I would absolutely check this out every time I factor by trial and error. Next thing, you factor 1. There's infinitely many different ways to factor 1, but the most sensible way is 1 and 1. So that ought to do the job for us. But it's always a good idea to double check this. So let's make this our check right here. Here to here is 2 sine x. Here to here is minus sine x. Those are like terms and they combine to a positive sine x. That's what we had, a positive sine x. And so that tells us the factorization is accurate. There's only one way to do it. The factorizations are always unique. And so we're in a good spot. Any questions, folks, with the factoring step?
How did you determine to put the negative sign in the left parenthesis?
Oh, that's a really good question. So the way I usually think about these is when I go to this step right here, I don't honestly have any clue where the negative sign is really going to go, but I did look ahead and decide I'm going to put a 1 and a 1 here, right? So then I was knowing or thinking ahead that this is my check, the outer product and the middle product, because all the fighting is really about getting that exactly right. That's where most of the work is in trial and error factoring. So I observed that if there was, let's say, a negative there, that would have been negative 2 sine x. We have to put a positive here. That's going to be a positive sine x. But these would add up to a negative right in that position. That tells us we are basically on the right track. If you're off by a negative sign, the next thing you do is you take your 2 sines and just flip them around. So now the outer product here to here is positive 2 sine x. Inner product here to here is negative sine x. And those two things do add up to the positive sine x that we were trying to gun for the whole time. So usually it's kind of a look before you leap kind of situation. Imagine what would happen with whatever you put here and see if you're getting close or far away from that.
Okay, thank you.
You bet. Other questions so far? Okay. One thing that people did ask about last class is this is factoring by trial and error, which is tricky. You could have just used the quadratic formula on this thing, but that is a lot of extra steps. Usually when I write down exam questions, it's always going to factor really nice like this. I don't want to make factoring a big part of the problem. This is a trigonometry class. But if you notice anything nasty in the homework, quadratic formula might not be a bad idea to give it a try. Well, we've done step 2. We moved all terms to the one side. We factored. Step 3 is use the zero product property and solve. In other words, this is a 1-step, or excuse me, a 3-step process where we're just trying to get to sine x equals something, a couple different equations. Zero product property happens right here. The only possible way that you multiplied two things and resulted in 0 for a real number system is if the first factor, 2 sine x minus 1, is 0, or if the second factor, sine x plus 1, is 0. Now we just solve both of those equations, and we're kind of well on our way on this problem. But this question is tricky, and using a double angle formula is something that's going to happen in the homework set as well. When you go to do the homework problems, you can look through the problems that we solved. There's some similar ones. And also, I encourage you to take a look at this right here. I also put down some hints on identities to try out on exercises 5 and 6, which are similar to what we're doing right here. If you lose your way, if it gets confusing and we're just not getting what we expect, don't hesitate to write. I'll be happy to help out. I know these are pretty tricky equations sometimes to get through. So now we're about ready to finish off the whole process. You want to solve for sine x in both of these equations. So over here, add 1, divide by 2, and you get that sine x equals 1/2. I'm going to color code that in green. That's been our pattern on these notes. That's a position we're going to search for on the y-axis. Same on this one, just subtract 1 from both sides. Sine x equals -1. That's right at the boundary where if this was, say, a -1.1, no solution at all. Even if it was -1.00001, no solution, and so on, the minimum you could solve for as an output is a -1 right here. Well, let's go and solve for those. The unit circle diagram makes its comeback once again. Because we're dealing with the sine function, we're plotting the values of 1/2 and -1 on the y-axis. So here's -1. Here's positive 1/2. And we need to find all angles that results in those outcomes. I think this one's not too bad. Anyone spot what this angle should be right here? Exactly. We have 3 pi over 2 corresponds to -1 for a sine function. Then over here at 1/2, this one's a little bit trickier, but if you draw out the diagram like this just seems plausible. It could be 30 degrees, right? And it's correct because sine at 1/2, sine at pi over 6 rather, gives you 1/2. The other angle is 5 pi over 6 over here. And because we're only searching for angles from 0 to 2 pi, we're done. We just have to state these outputs. We're solving for x and x here, so we can say x equals pi over 6, 5 pi over 6, 3 pi over 2. And we did it, folks. That's the full solution set if you're looking on a finite interval for that original equation. Well, any questions at all, folks, for that first equation of the day? Okay, so one down. Let's take a look at the next one. On the next equation, let's see here. It doesn't look friendly, right? But actually, even though it looks like a really nasty looking equation, it's not as bad as it seems. We just need some motivation on how to run through it. Any volunteers for what the right identity might be on this one? It just looks like a mess, right? Good call. This is an addition formula kind of problem. It could kind of tell if you see anything that goes like this. If you see 2 terms, 2 factors per term, it's probably the addition formula. Let's search along the notes because I mean, this is just the process. The moment you see this, open the document for trigonometric identities and just scan through them. It's good to stop right here. We're not going this far to the notes. We only put it here for a complete list. Then come back up. It's good to read these carefully because this is all about pattern recognition. The more you study those identities, the more you memorize about them, the easier it is to recognize that this is an identity. So even though some of these are provided on the real exam notes, when we go to take exam 3, I highly encourage you, make note cards, practice memorizing these. It helps out tremendously. You could, well, let me think about that. Not quite with the 7 theta there. What that's changing about the function is going to be the period. It's going to take something that looks like this, and 7 theta compresses it so it oscillates rapidly. But it's not necessarily changing, or there's nothing necessarily by periodicity you could simplify on the 7 thetas, 6 thetas, unless it was like 7 theta plus like 4 pi. Then you can just eliminate the 4 pi through periodicity. But what we could also do on this one is, let's see, it's cosine, cosine, sine, sine with a plus in the middle. It's that identity right there. So let's start by just writing it down on paper. Cosine, alpha minus beta, I'm just writing down the identity as it appeared, is equal to cosine alpha, cosine beta, plus, and let me temporarily move the participants window, sine alpha, sine beta. So that's our identity. And just doing this much right here, just writing it down on paper with your hand and a pencil, that's actually pretty good memorization as well. The more of your senses you involve in learning this math, writing down things, looking at it on paper, the easier it is to memorize. And turns out writing things down by your hand is a huge amount of things you're doing at once in your mind. It's helpful very much for memorization. So with this identity here, think of this as the alpha, that is the beta, and then again, it does go alpha beta, so we have to check that matches up. And this just says everything right here now turns into cosine. Identity says alpha minus beta, so we use our alpha, 7 theta, minus 6 theta, is now equal to the right-hand side, positive 1/2. That means this equation is basically example 1 that we did in these notes. We just had to use the right identity to get to that position. On the next step, add your like terms inside the cosine function. 7 theta minus 6 theta is just theta. I actually want to drop the color coding on that step. Let me fix that. This is just cosine theta set to 1/2. So same process as before. We go to the unit circle diagram. This time it's a cosine function, so 1/2 goes on the x-axis. Next thing, we're looking for the angles that takes us there. There's one angle up here. It looks like 60 degrees just by plotting it. It turns out that is accurate. Pi over 3 for 60 degrees, and cosine pi over 3 takes you to 1/2. This one is a reference angle, something over 3. Anyone recall what the numerator would be of this one? Good call, 5 pi over 3 for that one. And the moment you spot those two, you're done. You just have to state your answer. So don't celebrate too early. You still have to write theta equals pi over 3, 5 pi over 3. But once you get there, you're done. That's kind of weird. The last equation of the day is the fastest equation we solved in this entire set of notes. Part of that is because we practiced with example 1 of what the whole process looks like. But it's still kind of amazing. If you pick the right identity, these are not meant to be nasty, nasty problems. It's more pattern recognition, seeing what identity you can involve in each problem. Well, we did it, folks. That's solving trigonometric identities. Any questions at all with what we've done in these notes? Okay, and just to reemphasize, the homework section for this, it might not be too bad, but I'm sure that a lot of people are going to find equations that look like total mysteries. If that happens to you, don't hesitate to write. I'm a pretty fast typist, and I expect a lot of questions for this kind of material. And so I'll be there for you. If you have any questions, take a screenshot of your work, send it over to me and we can discuss the problem together. Well, let's now move over to the next topics for the course. I think I saved this twice, but oh well, that's good measure, I guess. We've now completed the core topics of a trigonometry course. So congratulations. I guess that's a good screen. This is a reminder that in chapter 8, we're now dealing with applications. So you're going to want to start getting fluent with these kinds of calculators. We're going to be using them more and more. So let's go back to the Moodle website. We're making an early start on section 8.1. So notice the due date is pretty far out there. We'll finish this one on Tuesday of next week. And section 8.1 will be for the law of sines. Section 8.2 will be for the law of cosines. And there's a myriad of other really interesting applications as well. So first, what's kind of interesting about these notes is that if you're going to discuss the law of sines, law of cosines, really what you need is that good formula for the area of a triangle. There's a lot of formulas, right? One of the formulas for any triangle is that area. It's 1/2 base times height. That's like our standard formula from geometry. You'd see in an algebra class. But what does this say? If A and B are lengths of two sides of a triangle, and theta is the angle included between those two sides, take a deep breath. That's a big statement. Before we do anything, let's capture this as a diagram. Sometimes when it comes to mathematics, this is a real skill in reading mathematics. And when you read mathematics like that, what was that again? Not quite, because with the radian measure, you'd have to give the equation of a circle going like this. It could be x squared arc length. It's not quite arc length, but it's pretty similar to the arc length formula. You know what? I think I'm getting a little foggy on that arc length formula. Let's take a look at it together. Arc length came up all the way back here, section 5.1. That's a good one to connect. It is a very similar angle, or formula rather. And the formula for arc length was this: 1/2 the radius squared and just the angle theta. So that's a good concept to connect. That's the area of just this wedge or the sector area. Arc length as a formula was just taking the radian measure and solving for s. So it was r times theta. But this one, which is an area formula, pretty similar to what we're dealing with right here. But we have additional things that we're complaining as well. Other questions about that so far? Okay, so we have this wild statement right here. But what do you want to do every time you read anything like that, whether it's this course or your future math classes? Draw a diagram immediately. In fact, when you're reading your textbook will draw those diagrams. I encourage you to just cover them up with paper. If you can make that diagram on your own, you're absorbing the material way better than just reading their diagram. You might make a mistake, but that's okay. You're learning as you make those mistakes. So let's make our own diagram. It says A and B are the lengths of two sides of a triangle. Let's just start by drawing a triangle. Now notice it says non-right triangles. So I'm going to try to draw a triangle that does not have any obvious 90-degree angle. It's kind of hard to do, it turns out. I would just naturally want to draw a 90-degree angle somewhere. Maybe go off this way and off this way. I think we kind of did it. Let me just fix this one a little bit better. Okay, so this is less than 90, more than 90. So I think we got it. That's a non-right triangle. A and B are the lengths of two sides of the triangle, and theta is the angle included between those two sides. They're saying that theta should be right here. Angle measurement between side A, side B. So this whole big statement in yellow gives us this as an outcome. Any questions, folks, to that stage? Okay, then they say the area of the triangle is this. And just reading that equation, that's a weird formula, right? This is the formula you would usually use, 1/2 base times height. So we want to resolve what in the world is going on with this. That thing right there is the secret to the law of sines. So if we can understand it, then we can write out the law of sines in a pretty short order. So what should we do? Let's use this formula instead and see if we can match up the formulas. So I'm going to write out area is 1/2 the base. We can let this be the base right here, if we like, times the height. We don't have a height. We need to actually include that in our diagram. If this is the base, we get a height by going from up here and dropping down a perpendicular, so there really is a right triangle. Now there's a right triangle in this diagram. In fact, there's two of them. There's a left-right triangle, and there's a right-hand right triangle. And this is the height h. So now we have the 1/2 and the b, so that part's right. It looks like it's all about h. We need to get that somehow expressed as something else in this equation up here. Well, here's the next thing we can do. We're going to hit the diagram that goes from here to here, the right diagram portion with SOHCAHTOA. Yeah, because we've dropped down a perpendicular, SOHCAHTOA is back on the table, but only for this portion of the triangle. It's not applying to this right here. We don't care about it as much. Sorry, say again. Well, this would be a 90-degree right here. Well, we're assisting when we drop down, because it's a height, this line right here has to be perpendicular. So this would be a 90-degree angle measurement. And we're just looking at this portion right here for SOHCAHTOA. But does that answer your question about that triangle? Gotcha. So if we hit this with SOHCAHTOA, well, there's a lot of stuff you could use. You could use cosine, you could use tangent. But for dealing with law of sines, we're going to use this part of SOHCAHTOA. It says sine of theta is going to be the opposite of theta. So theta, the opposite would be the height h right there. Divide by the hypotenuse. The hypotenuse would be this value a over here. So sine theta is h divided by a. Once we get to there, we have a formula for h. Just multiply both sides by a, and a sine theta equals h. So we're about to make a substitution, and once we make that substitution, we get area is 1/2 the base times our measurement for h, which is down here, a sine theta. Now these parentheses are just here to emphasize we made a substitution. We can drop them right here and say area is 1/2 a times b times sine theta. And so there it is. It's a pretty weird formula in all honesty, but it's a pretty effective formula. If you happen to know the angle theta, the measurement for A as a side length, measurement for the B as a side length, you can calculate the area of this triangle really fast without even knowing the height of the triangle. That's kind of impressive in a certain sense. It's so impressive, we ought to try it right away down below. But first, any questions, folks, with the derivation? Okay, this is kind of a friendly triangle down here in example 1. So we don't really need a calculator for anything on this, but you know, we're practicing with a calculator, so we'll still actually use it just to see how will this all go. 30 degrees is pi over 6, so sine at 30 degrees is just going to come out as a half. But we'll check that in our calculator as our first practice problem using a calculator. So it says compute the area of the following triangle. All we now need to do is, well, observe that we can compute the area. This formula, if you decide to use it, means you have to have an angle measurement, theta, and the side lengths A and B have to be adjacent to both of them. So for example, I'm going to fix the diagram in a moment, but if we had this problem, and this was a missing side length, you cannot even use this formula right above. You don't have the correct information. You might be able to do it if you can find that angle though, but the problem didn't supply it, so we're kind of stuck. Kreis, which was that again? The angle down here through trig? Potentially, but you'd have to also get a right triangle inside there. So it would be a little bit of work to get that angle in, but it could be done with the information that was given, absolutely. But that's the beauty of the angle or the identity that we have right here. It says you don't necessarily have to come up with any of these angles. If you have the right information, you'll just say that the area is 1/2. This is the A in the problem. This is the B in the problem. And that's the theta. So 1/2, 3 inches, times 2 inches, times sine at 30-degree measurement. And again, you could put pi/6 right here, but for applied problems like this, degree measurements seems to be more common than often. So we're going to use degree measurement as well. It's time for its fair share of work, I'd say. Now, next thing you want to do.
Sorry, I
Yes.
have one question. So like, does it matter where we put the A and B, as in like, can A be 2 inches and then B be 3 inches?
Yeah, absolutely. It would switch
Okay.
what's here and here, but that's going to be 6 no matter what you call your A or your B. So you can
Okay.
absolutely switch them. Yeah. Other questions at the moment? Okay, so if we were going to calculate this through a calculator, again, this is a practice problem. We know sine 30 degrees is sine pi/6. That's just a glorified 1/2. But the calculator, this is what you would do. Let me see if I can make this slightly easier to see side by side. First thing you want to do is in your calculator, hit your sine key. It's going to pull up. Oh dear, this is a little bit trickier than I was anticipating, but we'll get through it. It's going to pull up sine. There we go. Sine 30 is what you'll see in your calculator. And if you have a calculator with you right now, go ahead and punch that in and see what you get. I'm going to be using Desmos because for me, that's the easiest calculator to use to show to the class. You do, absolutely. So that's why I was saying in your calculator, put it in this way first to just see what happens. But for that comment right there, take a look at this region in your calculator. If you see something that says rad, it doesn't mean your calculator is radical or anything. It means you're in radian mode and you need to press that button right there. Press that button once and it'll change to deg per degree. So that's the hack around this one. For my calculator over here, this is what it's going to look like. Sine 30, and you can tell right away that's completely wrong, right? It's not negative 9.8803. If your calculator is saying that, you are in radian mode right here. You need to put in something else. In my calculator, I have to come down here to more options and, oh, did I? Yeah, it's the toggle right here for Desmos. Sorry, say again? Sorry, missed you that time. Oh, in the calculator. Oh, in here. I didn't know you could do that. That's kind of cool. Let me take a look. I'm not too sure. Let me take a look. DEG. Nah, doesn't look like they have any clue. That's one thing that's weird about these calculators is if you're writing this down on paper, you would absolutely put the degree symbol on it to emphasize this is degree measurement. But the calculator doesn't play around with that. You have to have degree mode set here for it to work out. On Desmos, I had a toggle degree, and if you're getting 0.5, your calculator is in the right mode. Are folks getting 0.5 as the output so far, if you have your calculator with you today? Doesn't sound like any issues, so let's move ahead.
So if you put in sine pi/6, would it generate 30 degrees?
It would, yeah. So over here, if you take, let me first take off the DEG there. If you punch this button, it's going to put it into rad mode. Oh, I keep on hitting the wrong thing. I'm not good with multiple windows, it turns out. If you're in rad mode, then you have to put inside here, like you said. Oh. A little tricky. Let's see here. I'll try to black this out just so we could get some good view of what the calculator would look like. This would be sine pi divide 6, and then you would get your 0.5. The way you get pi is you take this and just hit that key, then divide by 6, and you'll get that as an output. I'm not sure what just happened there. And then you'd be all set. Yep, you betcha. Let me see if I can black this out a little bit better. There we go. Well, whatever way we do it, we're going to get at 1/2 of this position. I won't be practicing with the calculator more and more. I'm going to try to find a better, more sensible way to make this happen without too many issues. But this is the result you're going to get. 1/2 times 3 inches times 2 inches. Sine at 30 degrees or sine at pi over 6 gives you 0.5 or 1/2 again. So now we have a cancellation from this 2 and that 2, and 3 times 0.5 will give us 1.5 inches squared. So that's finding the angular area of this rectangle or triangle as fast as possible. Well, any last questions, folks, on running through this one? Okay, so we did it, and I've mentioned that when you look at that equation right there, that's basically law of sines. And because that's such an important concept, let's derive it ourselves. We're going to do the law of sines. To get a feel for where it even comes from, but yeah, you could go right here. This is the law of sines. And it's not too bad looking at it from that point of view, but when you look at that, it's not very clear what at all is really happening with the law of sines. I have a triple-sided equation here, reciprocal it, so another triple-sided equation. It's some really mysterious stuff. So to get to that point, we'll derive it ourselves to see where all this stuff comes from. The hint is, it comes from that in a really weird way. So first thing we're going to do is pull this in as a screenshot to help us work with it. Now that we have that, we're also going to need just a generic triangle. We want to try to draw it so it's not a right triangle. So again, I'll just try my best. I naturally seem to want to draw angles with 90 degrees in it. It's actually kind of hard for some reason. So there's our triangle. Next thing we have to put in here is some angle measurements. And here's some common ones you would see in the law of sines. You would put, say, an angle alpha here. That would be that angle measurement. But the moment you place alpha, you want to place the side length A opposite of it just immediately. So this is the Greek letter alpha, and you learn lots of Greek in a trigonometry class. Here's part of the reason why. Next angle we're going to put down is beta for this position. So this one is beta. And the final, well, before we get there, the moment you place beta, you want to go to the opposite side and put down side length B. So the correspondence of angle with its opposite is one of the most important things for both law of sines and law of cosines all at once. Let me make that a better looking alpha. Last angle is going to be gamma. And that's the first 3 letters of the Greek alphabet, alpha, beta, gamma. So congratulations. At least I think it is. I'm not Greek, so correct me if I'm wrong. So opposite side of gamma would be the letter C. And with that diagram set, what we're going to use is this area formula 3 different times. And you can do that because you could use it for the angle alpha, beta, and gamma. It's not so much about the A, B sine theta. This formula is all about the pattern that you put everything together. So looking at the diagram above, if you put down area is 1/2, let's say we're based off the angle alpha right there. The side lengths that you would have to use are B and C, the 2 sides adjacent to alpha. And then you just multiply it by sine alpha. So on one hand, That's the area of this rectangle. I keep saying rectangle. Let me try again. That's the area of this triangle through the formula below. And then we just do it again for beta. On the other hand, area is 1/2. We take the sides adjacent to beta, A times C, and then take sine of the angle included between the two of them, beta. And then just do it again. One more time at gamma. Area equals, take the two adjacent sides, A times B, and calculate sine at gamma. So we use that area formula 3 different times. That's the pattern. And the area you see here is the exact area every single time we did it. This implies we can equate all 3 sides. 1/2 BC sine alpha is now equal to 1/2 A times C times sine beta, which is finally also equal to, oh, that's a typo, isn't it? Let's fix that one. A 1/2 goes there, so now it's good to double check your work as you write them down. It's equal to this 1/2 AB sine gamma. So here is the derivation so far, but it's still not the law of sines. To get the law of sines, we want to clear that denominator, the 2, the 2, the 2. So how you do it, on the left-hand side, you have to multiply by 2. But that means you must multiply every side of this equation by 2. The middle side and the far right-hand side. So that clears our denominators. That's going to help out. And now the next thing we want to eliminate is the BC, the AC, and the AB all at once. And how we do that is we're just going to divide by ABC on every single equation. So we're pretty much there. We're ready to give a conclusion, and that conclusion is the law of sines. First, let's show the cancellations. These two are just going to completely annihilate. On the first term, BC's are gone. On the, not first term, but the left-hand side of the equation. On the middle side of the equation, A and C are gone. And the right-hand side of the equation, A and B are gone. And all we're doing to derive the law of sines at this point is just writing down the sole survivors. It is sine alpha over alpha. And notice that pattern. You have alpha and its adjacent side A. You're just taking sine of one end, dividing by the other end. Oh, let's fix that. That should be an A, not an alpha. So that's our first one. Over here, this is going to be set equal to sine beta divided by B. And looking at the triangle, that's just taking sine of this side divided by the opposite side. So the actual symbols you use, whether they're Greek, whether they're something else, Mandarin, it's totally irrelevant. It's about this pattern you see right here. You take sine of one angle, just divide by the opposite side, and you're doing the law of sines. So last one. We have sine gamma divide by C, and looking at the diagram, that's sine of this angle, divide by the opposite side C, and that's all you do in law of sines. It's a triple-sided equation, which is kind of odd, but when you go to use this equation, we'll be using it on Thursday, we only use 2 sides at once. So we don't always use all 3 sides. We just look at what information is given, pick 2 sides. Maybe it's the first 2, or maybe it's the outer 2, or the far right 2. Just use whichever sides of this equation is relevant to the problem at hand. And that's exactly what we'll be practicing when we come back on Tuesday. Definitely don't forget your calculator. We'll be using it a whole lot. And we're emphasizing this in the class because we'll need to do it when we're taking the exam as well. But any last questions, folks, before we call it a night?
I don't have a question about this, but I have a question about today's homework, like the assignment 10, the last problem.
Well, since class is over, we'll have to end class officially, but just hang on in the Zoom meeting. And I always help out with any questions right after. So just stick
Okay.
around and I'll be happy to help.
Okay.
Any other questions, folks, before we call tonight? Okay, have a great night, everyone, and I'll see you all on Tuesday's class. So let me
Thank you.
close this out and not forget to save it. Yep, have a great one, folks. And which section were you looking at?